Okay, so let's start. Any questions from the previous class? No questions? Okay. So in the last class, we were looking at different numerical algorithms for solving unconstrained minimization problems. And essentially, we were looking at variants of the gradient descent algorithm. So recall that the gradient descent, what you do is, in fact, in any general descent algorithm, it's an iterative process wherein at each step you're given a point, and from that point you compute the descent direction, basically a direction wherein you're sure that the function value decreases. And you keep trying to, and you take a step in that particular direction. The amount you move in that particular direction is given by the step size. So you're iteratively trying to go down the hill, essentially. If you choose the directions, so typically gradient descent refers to a case where you take the descent direction to be that of a negative gradient. Right? And that will be the direction where the descent is the maximum. Correct? Maximum in a certain sense. So in gradient descent, you always iterate xt equal to xt minus 1 plus some delta t times the negative of the gradient. Now, how do you choose this step size? Either you can choose this to be a constant, as we've seen, or you can try to optimize the step size either by running an exact search, an exact line search, or you can try something like a backtracking line search. The backtracking line search is a more efficient way of finding the best step size and is computationally less complex than the exact line search. Recall that in the backtracking line search, you only need to compute the function multiple times, whereas if you wanted to do something like exact line search, you would at least need to compute the gradient, which is typically more expensive than computing the function. So we saw some interpretations as to why the backtracking line search can work. Okay. So in today's class, let's see a few examples, and I'll also introduce some more algorithms for minimizing unconstrained functions, so unconstrained minimization of convex functions, and then we'll get into how do you solve constrained minimization problems with equality constraints. So we'll build things step by step. Once we have algorithms for unconstrained minimization, we'll see that it's not very difficult to extend this to algorithms for minimization with equality constraints. But then we need some more ideas in order to get to inequality constraints. Okay. So let's take the standard example, one that you've already seen in your assignment, of least squares. Right. So the least squares problem, recall, is the following. So the least squares problem is to minimize overall x in Rn of the 2 norm of ax minus b. So 2 norm the whole square of ax minus b. So our function f0 of x is 2 norm of ax minus b the whole square. What is the gradient? Are 2 times but then is the norm a differentiable function? Yes, an easier way is to just write this as ax minus b transpose ax minus b, expand that out, basically get a quadratic form. So what will be the gradient? 2 times A transpose AX minus 2 A transpose B. And what is the HCM? Two times A transpose A. The least squares problem is one where we know we have a closed form expression for the solution, right? And what is the closed form expression equal to? So X star is basically A transpose A third inverse times A transpose B. So we're typically looking at problems wherein Ax equal to B does not have a solution. So the goal is to find the best X which minimizes the two norms square. Okay. So let's try to solve this using gradient descent with both constant step size and also step size with backtracking and such. Okay. So how would we do that? So I'll write some functions just to compute the gradient, the Hessian and the function itself. Okay. The gradient is just 2 times A transpose AX minus 2 times A transpose B. The Hessian is just 2 times A transpose A, and the function just computes AX minus B, the two norms square. Okay. So for this, let me take a simple 5 by, let's start with a 5 by 3 matrix A. Any questions? Let's start with the 5 by 3 matrix A. I'll generate A randomly, just to make sure that A is a full rank matrix. And B, I'll just set it to be equal to 1, 1, 3, 2, 2. I'm sure that this will not have a solution, right? Because the first and the second rows of A are going to be different with probability 1, and I'm setting B of 1 to be equal to 1 and B of 2 to be equal to 1. And so let's see what I get. So it so happens that the optimal solution, that is A transpose A the whole inverse into A transpose B, is this particular vector over here, and the minimum value of the function turns out to be 3.88. So now let's write down the gradient descent algorithm. Okay, I want to write down this function that's gradient descent with a constant step size. So let's fix a step size of 0.05. I don't know anything else about the problem, so I'll just fix it to be something. And I'll keep running, so basically I have to iterate. So I'll keep running the iteration until the value of the function does not change significantly. And I'll set that from the previous iteration to the next iteration, if the difference is less than this threshold, then I'll stop. Okay. So I need to choose, let's say, current X. Let me fix that. So this function takes 3 inputs. One is A and B, and the third is this initial point, the point from which I start my gradient descent algorithm. I'm keeping this as an input to the function just because when I compare different types of methods, I want to always start from the same point and see whether it converges, how long it takes to converge from that given starting point. Because otherwise, I don't know. From certain starting points, it may converge faster. From certain starting points, it may converge slower. So I want to always start at the same point. So I'll set the current X to be the initial point. We'll need this. And current loss, we'll just set that to be something. So if the loss doesn't change much, that is the function value does not change much from the previous iteration to the next iteration, then I stop. Otherwise I continue. Right. So for gradient descent, I need to, for any descent algorithm, I need to first fix the descent direction. And this is just equal to the negative of the gradient. And it's evaluated at the current value fixed. And the step size is always fixed, it's equal to 0.05. So the next x is equal to current x plus step size times the descent direction. So this is the next value, and I'm going to set current x. And I also need to know what is the function value. Function of a b. Oh, that's the correct x. And I'll set function of and I just return the value of the loss. That's fine. So let's see, let's just plot and see what this looks like. So it happens to take, it decays at an exponential rate, and it happens to take around 50 odd iterations to converge. This pink curve corresponds to the minimum value, and the blue curve is what I get using gradient descent. Legend. Okay. And so this is one approach wherein we use gradient descent with a constant step size. Now I just make a copy of this and try to modify it to do backtracking line search. So initially I'm going to set my step size to be equal to 1, but I also need two other constants, right? Recall that I need an alpha and a beta. I'll set let's quickly take a look at the backtracking line search algorithm. In backtracking line search, you start with step size equal to 1, delta equal to 1, and you fix these two constants, alpha between 0 and 1 and beta between 0 and half. So let me just choose alpha equal to say 0.9 and beta to be equal to 0.4. Okay. And once you compute a descent direction, you want to compute the best step size, or at least an approximately best step size. So you keep iterating as long as f of x, the current point, plus delta times u is greater than this first order approximation, which is f of x plus beta times delta times gradient inner product with u. You decrease the value of delta by a factor of r. Okay. So let's write that. So we compute the descent direction. The descent direction is basically the negative of the gradient. In fact, let's say gradient vector to be equal to x, and I'll set the descent direction to be the negative of gradient. Now I need to compute the step size. I'll start with step size equal to 1, and I need to check for the following condition. The condition is f of xt plus step size times the descent direction, f of xt, which is current x, plus step size times descent direction, as long as this is greater than f of xt plus, this is f of xt, plus beta times delta. Beta times delta is the step size, times the inner product between the gradient and the descent direction. So as long as this happens, I keep decreasing the step size. So step size equal to step size into alpha. So that's what I do, and the rest is essentially the same. Nothing changes in the rest of the algorithm. It's only the only difference between backtracking line search and the previous thing was how I choose the step size. So keep everything else the same. And let me plot both the one with constant step size and factor. You see that with backtracking line search, it converges much faster. Right? The blue curve corresponds to the one with constant step size, whereas the orange line corresponds to the algorithm with backtracking line search. So it's much better. In fact, you can try to derive the bounds on the number of iterations required to converge. Right? You can take a look at the book by Boyd and Vandenberg, where there's a more detailed analysis of convergence of various such algorithms. You can prove that with backtracking line search you can do much better. Well, in fact, if you think about it, the constant step size, there's no guarantee that you will even converge. If the step size is not large enough, is not small enough, with constant step size, you could potentially keep oscillating. In particular, if the step size is much larger than something times the threshold, right? If you keep a very small threshold, then potentially you keep oscillating. How these are affected by convexity? Well, I could take a non-convex function in this case, but all I would be guaranteed is that I will converge to a local minimum. Right? There's nothing more I can hope to get. What do you mean? Okay. Correct. So you have algorithms, for example, algorithms like gradient descent that will converge to some local minimum. But that's the best that you can guarantee with this. You can never say that it will converge to the global minimum. So I guess what you are trying to say is that suppose that your region is bounded. Right? Suppose you are trying to perform minimization over a bounded region, even if it is a non-convex function, if it's a non-convex, it's a non-convex optimization problem over a bounded region. That's what we're talking about, right? In this case, true, you could potentially come up with an algorithm that converges to the global minimum. But in fact, if you consider the class, even if it's a bounded interval, let's just take class of all functions in, let's say, a cube, right, of side length 1 in high dimensions. We're always interested in high dimensional optimization problems. Then you can prove a sort of a negative result that you cannot do this efficiently. There is no polynomial time algorithm that will find the global minimum for arbitrary non-convex functions. That's what I said. If it's a convex optimization problem, then you can solve it efficiently. It can be solved in polynomial time. But if it's a non-convex optimization problem, we can go to a local minimum in polynomial time. That is something that is guaranteed by these descent methods. Now there are certain classes of non-convex optimization problems that you could still solve in polynomial time. But you would need to know something about the problem itself. Maybe you know that there are only these many local minima. Because what can so happen is that there can be a large number of local minima. So how do you know which one to get to? Correct. We've already seen proof, right? That how many stationary points does a convex function have? 1. So if there is a local minimum, then that should be the global minimum. So either the function does not have a local minimum, because the minimum could be achieved at say minus infinity, or there exists a local minimum and that is going to be the global minimum. X power 4, is it convex? Why? Okay, how do you verify whether X power 4 is convex or not? Okay, what is second derivative? Okay, and what can you say about X square? It's always greater than or equal to 0. So it's convex. Okay. How many stationary points does this have? There's only one stationary point, that is at x equal to 0. So then that is the local, that is the local minimum and also a global minimum. So what are conditions for a saddle point? Or suppose I give you a stationary point. When can you say that that is the local minimum? So suppose I give you, it's a smooth differentiable function, and I tell you that it's a local minimum, or I say that it's a stationary point. So the gradient is equal to 0. How do you verify whether it is a local minimum or not? Does the first derivative test tell you whether it's a local minimum or a local maximum or a saddle point? You need a second derivative test. So what does second derivative test do? It's a local minimum. Suppose the function is convex. Then exactly. So that should be a local minimum. Right? Okay. Okay. Can you tell me whether that can be a saddle point? Suppose if you know that the function is convex, you don't know then sure, but you can't really say whether it's a local minimum or a local maximum. Potentially yes. Yes. But if you know that the function is convex, then for sure it is going to be a local minimum. The function is convex. So it cannot have anything other than a global minimum. So along some direction the function should be convex, along some direction the function should be concave. Okay, that's exactly what it means. I mean, for a two-dimensional surface or a function in two variables, a saddle point is precisely that. Along some direction it is convex and along some direction it is concave. It looks like a saddle. What does it mean? What do you mean by saddle point for a function of one variable? Okay. Okay. So there's one direction along which the function is convex, there's another direction along which the function is concave. Okay, what is x cube convex? Is it concave? I'm sorry? Yes. I'm starting both of them because I'm taking this initial point as one of the inputs. Which one? I think the initial point, yes, but then it could take a different trajectory. Right? So I start with an initial point, that is x0. But in both of these algorithms, x1 will be different. The only point is that when I do backtracking, it will converge to x1 is going to be closer to the minimum than the case when I have a constant step size. It will just get to the minimum point faster. I'm sorry? Okay, so maybe I should have been more careful. So when I'm plotting, I'm actually not plotting from the initial point. I should perhaps put this here. So let's say yes. Let me compute function at the initial point. I've actually plotted from x1 onwards. Let me do plot it from x0 onwards. Now both of them start from the same point. Any other questions? Okay. So these are two algorithms, gradient descent algorithms, and you know one converges faster. Is there any scope of doing even better than this? Now, of course, I could use exact line search instead of backtracking line search, and potentially I could converge even faster. But as you know, that has a much higher complexity. Okay. So let's see two other classes of algorithms. One which is very close to this, and that is steepest descent. Now, in all of these algorithms, the basic principle is still the same. You find the descent direction, you find the step size, and then you move in that particular direction with that particular step size. Okay. The question is, how do you choose your descent direction? In the method of steepest descent, formally, the descent direction is chosen as follows. So let me call that U. For the normalized steepest descent direction, and this is said to be equal to min of of U less than or equal to 1, or let me set U equal to 1, of the inner product between U and the gradient of x. Okay. Just this, the positive. The key point to note here is that this, when I say norm of U equal to 1, this need not necessarily be the Euclidean norm. This could be any norm. And each norm is going to give you another method, a different method for steepest descent. If I choose a Euclidean norm, then what is the U that minimizes this?
mod of the gradient
Okay.
and find the largest value.
Gradient mod of the gradient.
So I think each of those terms just take the magnitudes.
In magnitudes of the components of the gradient. Okay.
Whichever is the highest value.
Okay.
Let's say that I'm the index 9.
Okay.
For you at that index, you can get max.
That won't be what you get if you use the Euclidean. So this is going to be the negative of the gradient, right? Or the negative of the gradient normalized. So if you take the Euclidean norm, then U NSD will just be the negative of the gradient of f of x divided by the 2 norm of f of x. And we'll just end up with standard gradient descent, nothing else. When you choose the step size, either you can choose a constant step size or you can do backtracking line search. What if I choose the L1 now? If I choose the L1 now, I get exactly what you mentioned. So the U turns out to be an indicator vector. Along, you take the magnitude of the large, basically you take that component which has the largest magnitude and move in the direction negative to that of that component in gradient f of x. So in this case, U NSD is basically going to be equal to, so you first find some I star, so the largest component of the gradient in absolute value, and you set your NSP to be the ith indicator vector multiplied by the sign of the ith component. So this is sometimes called coordinate descent. Which one? It's normal. It first one norm 1. So the advantage of something like coordinate descent is that it's very efficient, because you're only moving along one direction, along one component. There's only one component to change, you leave the rest of the components exactly as it is. What does?
What does ST stand for?
NSD normalized steepest descent. Normalized because I'm taking the norm to be equal to 1. I can also consider the following norm, which is norm of x is equal to the 2 norm of some, let's say, t to the half times x. So you pick a positive semi-definite matrix P, and you define the norm of x to be the square root of the PSD matrix, the 2 norm of the square root of the PSD matrix times x. That's our way of saying that the norm x square is just equal to x transpose px. So where p is positive definite, not just PSD. Let me call this positive definite matrix. In this case, you can show, I mean, I'm not going to derive it, but you can show that the direction of u in SD happens to be equal to p to the minus half times x divided by the 2 norm of p to the minus half times x. So with the negative sign. So this is almost like a gradient descent, but you can view this as gradient descent with a coordinate transformation, because you are multiplying with some full rank matrix, which is as good as doing coordinate transformation plus standard gradient descent. So you do a change of basis followed by gradient descent and this one. Because that's one interpretation of this particular steepest descent. So again, you can choose different norms and you will get a different steepest descent method. I'm sorry? I don't think there's a specific name for this because it's whatever, a norm that is defined by a matrix. Alright. So, but in many cases, this may or may not give you improvement in terms of convergence time. But what will give you improvement is if you have more information about the function itself. So previously what we saw were these gradient descent type of algorithms where we had knowledge of the zeroth and the first order properties of the function. So they are called first order methods because they use the function value itself and the first derivative, which is the gradient. But if you have more information, so for example, if it is twice differentiable and you can compute the Hessian, then you have these so-called second order methods. And one such second order method is the Newton's method. And we've seen Newton's method previously when we dealt with minimizing functions of one variable. And the basic idea behind Newton's method is you first look at the second order approximation, the second order Taylor series approximation to the given function, and at each step you try to minimize the second order approximation. So the second order approximation is just going to be a quadratic, and we try to minimize that quadratic function, which we know very well how to do. Right? So, basic principle. Look at the second order Taylor series expansion. So suppose you have, for a given point xt, in the current iteration, the tth iteration, you have some point xt, and you look at this function f tilde of xt, or I call this f tilde of u. Let me call this v instead, because I need u for something else. Which is equal to f of xt plus v transpose times the gradient f of xt plus half v transpose Hessian f of xt times v. So you fix a particular xt and you look at the function in the neighborhood of xt. So v is basically, we want to determine the best direction to move, correct? And that v will tell us which direction to move. So of course the function is not, the function f of v is not exactly equal to this. So this is supposed to be a crude approximation to f of xt plus v. So an approximation of f of xt plus v, we just look at the first two terms in the Taylor series expansion. This is a nice quadratic function. What more can you say? Can you say that this is always going to be convex? Yeah? So remember, there are two things, right? One is the function f and the function f tilde. When can the f tilde is a quadratic function? If the variable is v. Right? F could generally be any arbitrary function. When can I guarantee that f tilde is going to be convex? If y? Correct. So basically the Hessian of f tilde is going to be equal to the Hessian of f. So if f is convex at every point in the domain, then for every xt, f tilde is going to be convex. Okay. So this is convex if f is convex. So how to minimize? So the goal is to minimize f tilde. Overall possibility. And we can do this by taking the gradient, setting it to be equal to 0, because this is a convex function. Right? And what will the v star be equal to? What is the minimizer? What is the gradient of f tilde going to be equal to? Yeah, so the gradient of this is going to be gradient f of xt plus gradient the Hessian times v. So v is equal to the negative of, gradient I can't really divide. Remember that the Hessian is a matrix. So this will be the Hessian f of x inverse times the gradient f of x. So you have to be careful here, whether you're pre-multiplying or post-multiplying by the matrix. Okay. So all of this works only if the Hessian matrix is invertible. That's a strong constraint on the Newton structure. Sorry? Not necessarily, right? So when is the function convex? If the Hessian matrix is positive semi-definite. So it could potentially have zero eigenvalues. So you can use the Newton's method only at points where you know that this is going to be positive definite. Let's repeat on. So this is your descent direction. Remember that it's different from what we had previously. Earlier we took gradient f of x, negative of the gradient of f of x to be a descent direction, but now we are going to take negative of the inverse of the Hessian times the gradient. Okay. So let's see how this performs for our problem, our least squares optimization problem. Okay, before that, so this gives us the descent direction. How do we update x? So our update the Newton update is going to be the following. So you set x t to be equal to x t minus 1. Let me call this v star of xt. Right, because this v star depends on xt. So xt minus 1 plus some, let me call it delta t times v star of xt minus 1. Where I can either set delta t to be equal to 1 or constant, or I can also set it to be, I could choose the best delta t based on line search. So delta t equal to 1, this is sometimes called the pure Newton method. And if delta t is not equal to 1, typically chosen using line search, then you get the so-called damped Newton method. Damped or guarded. So let's implement the damped Newton method with backtracking line search. So I start with a step size of 1, and effectively everything else remains the same except the computation of the descent direction. Oops. So we'll start with a step size, a certain step size. The descent direction is going to be the inverse of the Hessian times the gradient. Right? The negative of the inverse of the Hessian times the gradient. The inverse of the Hessian times the gradient. So the inverse of Hessian times the gradient. And everything else is the same. I'm not going to change anything else. Okay, so Newton. Compute Hessian of A, B, X times the gradient. Okay, so that's fine. And let's see how each of these perform. I don't really need anything else. Hessian only depends on A in this case. So the blue curve is the gradient descent with constant step size. The orange curve is gradient descent with backtracking line search. And the green curve is constant step size. And in this case, the Newton's method converges in one step. Why do you think that's the case? Exactly, because our objective function is quadratic. And what does the Newton method do? It tries to approximate it by a quadratic function and solves it exactly. So in this case, I am getting the exact minimum value in one step. In general, if your function is not quadratic, of course, you will not get the exact solution in one step, but usually it will converge faster than gradient descent. Okay. Any questions? Okay. So all of this was for unconstrained minimization. So now let's see how do we extend this to constrained minimization problems. And in fact, the best algorithm to extend to equality constrained minimization is Newton's method. So we see that with almost no effort, we can extend this to equality constrained minimization problems. If the goal is to minimize some function f of x subject to the constraints that, let's say, ax is equal to b. So we don't have any inequality constraints, just equality constraints. And specifically, I'm going to use Newton's method. So all of these methods, when you have constrained minimization problems, the fundamental assumption is that you are able to find at least one point that satisfies all of the constraints. So your initial point has to be something that satisfies all of the constraints. Otherwise, you can't do anything. So you can't really solve satisfiability problems using this. So you always start with assume that we have xt that satisfies 8 times xt equal to b. So what is the goal? I want to choose I want to be able to compute some x t plus 1 such that first it has to satisfy the constraint. So a times xt plus 1 should be equal to b, and the second is that somehow f of xt plus 1 should be less than or equal to f of xt. You want to descend, you don't want to ascend. So effectively this boils down to some sort of other constraint optimization problem that you can try to solve using Lagrange multipliers. So, I mean, the problem doesn't become any easier as it is. So if you look at the Newton approximation, the Taylor series approximation. So we know that we have an xt which satisfies these constraints. So we look at the Taylor series expansion, f, let's call this f tilde xt of v, which is equal to f of xt plus v transpose the gradient f of xt plus half v transpose Hessian of f at xt times v. So what we want to do is minimize. Let us try to solve the simpler problem of minimization over v of f tilde of v subject to the constraint that a times xt plus v is equal to b. Right? But xt is fixed and we know that a times xt should be equal to b. So what should a times v be equal to? B minus a times xt, which is 0, right? So we want a v that lies in the right null space of A. Of course, the assumption is that you have infinitely many solutions to A times x equal to b. So the null space is not trivial. Okay, is that clear? What's your objective? So we have this original problem of minimization of an arbitrary convex function subject to equality constraint, subject to the constraint that ax is equal to b. In Newton's method, the principle is you try to solve an easier problem of minimizing the quadratic function subject to the constraint that a times v is equal to 0. So from convex minimization problem subject to equality constraints, I boiled it down to quadratic minimization problems with equality linear constraints. Okay. And you keep doing this at each step. So how do we solve this particular quadratic minimization problem? I can't just set the gradient to be equal to 0, right? Because it's not an unconstrained minimization problem. So what is the standard to Lagrange multiplier, so solve for the KKT conditions. So I only have inequality constraints. I don't have any, I only have equality constraints, no inequality constraints at all. That makes it much simpler. So what is the Lagrangian equal to? So this is a function of v for a given xt, of course. This is a function of v, and I will define Lagrangian. Let me call it w. Okay, so this will be equal to f tilde xt of v plus w transpose a. Right? Okay, so then the goal is, what would the KKT conditions be for this? So a times b should be equal to 0. The gradient of the Lagrangian with respect to v, L of v comma w, this should be equal to 0. Do you need w greater than or equal to 0? No, right? Because I don't have any inequality constraints. So w can be an arbitrary real vector. Anything else? Nothing else. Okay, so that's all that we require. So what do I get from the first condition is straightforward, nothing to be done there. What is this going to be equal to? Yeah, so it will be equal to the gradient of f of xt plus the Hessian f of xt times v plus a transpose times w. So this should be equal to 0. Right? So I can say that the Hessian f of xt plus a transpose w should be equal to the negative of the gradient of f of xt. Where w is now another set of variables, so don't really require, but I'm still going to keep it. So, times it. Right? So I have these two sets of linear equations, I will solve for them. So if I combine these two, I can write this as Hessian of f evaluated at xt, a transpose a 0 times v w. Right? I'm just combining these two equations, this equation and this equation, and writing them in one big matrix form. So this should be equal to the negative of the gradient of f evaluated at xt and 0. Right? So I can get v, which is my next step. So v star is just going to be the first, if I'm looking at Rn, then v is going to be the first n elements of this inverse times this. I'm sorry? Right now I'm assuming there's convex optimization and is satisfies from there. All of this is under those assumptions. Even otherwise, it's an algorithm. It may converge, it may not converge to anything at all, but I can still apply this algorithm. We don't know, right? If there are absolutely no guarantees given, then you can't really say anything. But this requires something stronger, and that's something to keep in mind, that this matrix should be invertible. Which is one step beyond asking this Hessian to be invertible. So in particular, A should be full rank, that is necessary. Hessian should be invertible, the A should be full rank, but that's not sufficient, remember, because it's not enough because the rows of, if the rows of A are linearly dependent when you combine them with the Hessian, then you can't really invert this matrix. So your V star is, we call this V star of xt. This is equal to, you take this matrix F of Hessian A transpose A 0 inverse times gradient F of xt. So 0, and I want to look at the first n elements of this vector. Right? So this involves higher computational complexity than anything we've seen so far. It requires you to be able to invert an n plus whatever m by n plus n matrix, assuming that there are m constraints. So once again, our xt plus 1 is going to be equal to xt plus delta t times v star of x. So this is going to be our update set. Where again I can choose my delta t to be equal to 1, that will give me the pure Newton method, or the damped Newton method where I can choose delta t, typically using backtracking research. So with this, we know exactly how to solve any, or numerically solve any convex optimization problem with equality constraints. In fact, not just convex, you could also use it for non-convex optimization problems. Right? But I have to be careful because I'm assuming that the function is kind of locally convex, and you start with a starting point, you start with an initial point where the function is convex, so that you keep moving in the direction of the Hessian, right? So sorry, in the direction of the local minimum. Okay. If the can you repeat? Okay.
And the function is ordered.
Okay.
And the direction is not constant.
Okay.
Then
Well, you don't have to do, you can't give any guarantees. So non-convex optimization problems are hard in general. Some guarantees can be given in the sense that you can say when it converges to a local minimum. If it converges, it's going to be very efficient. It's not going to take a long time to converge. But beyond that, you can't say anything. At least using these particular methods. Any other questions? So now we are almost there. We need some approaches to be able to solve inequality constraints, problems with inequality constraints. Now, in general, that's going to be hard because so far we have this exact approach that we can use. So, how do we solve problems with inequality constraints? I'll just give a brief overview of the kind of techniques that are used. The broad class of techniques that are used to solve problems with inequality constraints are these so-called barrier methods. wherein you try to ensure, of course, first you have to start with a point inside your constraint set, and you modify your objective function by setting this artificial barrier, which ensures that no matter what you do, you never go outside the constraint set. And let's see how we can do that.
First order methods that can solve the equality constraint.
I'm sorry, which one?
Like, different method is
The second order method, yes.
I don't know first order methods that can be used to
Solve what?
constraint.
There are, but this is sort of the easiest way to be able to solve this. And in fact, it gives you a nice closed form expression. So we just focus on this for this purpose. Again, this is what I talked about is in no way representative of the kind of algorithms that are present for solving constraint optimization or even unconstrained optimization techniques. There are many algorithms that can be used. These are just a sample of some algorithms. Just one algorithm for each case. That's all that I'm going to be able to introduce in this course. But even Boyd and Vandenberg has a nice collection of algorithms. There are like a few chapters on how do you solve unconstrained problems with equality constraints and with inequality constraints. Okay, so let's suppose that we have an optimization problem in standard form. So minimize some f0 of x. Let's say that I have only one inequality constraint, f1 of x less than or equal to 0, and some equality constraints. Let's not bother about equality constraints because we know how to handle those. Okay? So how do we solve this particular problem? The fundamental idea is the following. So you have this, you first start with some x0 which you know lies inside the constraint set. So suppose we have some x2 which satisfies the inequality constraint. F1 of x is strictly less than 0. I'm not happy with something that just satisfies less than or equal to 0. It lies in the interior. So if I have more than one inequality constraint, I want to ensure that there exists some point which lies strictly in the interior. That is, all of the f of fi of xt is strictly less than 0. So in other words, what condition does the optimization problem have to solve? So it has to satisfy Slater's condition. So I'm assuming that we have a problem which satisfies Slater's condition, and I'm able to get a point which satisfies all the inequality constraints with strict inequality. Okay. So the goal is to find some xt plus 1 such that f1 of x t plus 1 is also less than 0 and f1 of xt plus 1 is less than or equal to, f0 of xt plus 1 is less than or equal to f0 of xt. To do so, we'll modify this by considering, let me call this f bar of x, which is equal to f0 of x plus some g of f1 of x. Okay, where this g is what I call a barrier function. So g of P of U is something which is finite for U less than 0, and it takes the value plus infinity at U equal to 0. One classical example is log 1 by x, right? Or I should say log of minus x. So for x negative, it satisfies, so it's finite, but as you approach 0, this tends to infinity. Correct? So this ensures that at any point the objective function is such that it will never let you go outside the constraints. It keeps you strictly inside this. But now you have this additional function over here. So what you're minimizing is not f0 of x exactly. Now that's a problem, right? So you perform this sort of iterative method where at each step you look at ft bar of x, which is the true objective function plus something times this barrier function. And we choose this epsilon t such that as t progresses, epsilon t tends to 0. Because it may so happen that for your constraint optimization problem, the optimum point is actually at the boundary, not an interior point. That can very well happen, right? So what these approaches do is you first try to look for points in the interior. If there's a minimum, well and good, you will converge to that. If not, then this epsilon t will tend to 0, and eventually you will reach some point that is close to the boundary. So that's the intuitive approach for, or the intuition behind these barrier methods. Right? So maybe let's stop here. Any questions?